Let's talk about power series solutions of first-order differential equations. Find the first four non-zero terms in a power series expansion about x equals 0 as a general solution to the differential equation y prime plus x plus 2y equals 0. Well, if we want a power series solution, let's let y equal the power series. So y is the sum as n goes from 0 to infinity of a sub n, x to the n. Notice we're expanding about x equals 0, so it's not x minus 2 to the n or x minus 5 to the n, it's just x to the n. And this differential equation also has a y prime in it, so we need to find a series for y prime. Let's just take the derivative of both sides. We end up with y prime equals the sum as n goes from 0 to infinity of a sub n, and x to the n minus 1. That's just going to be the derivative of x to the n. So here's our differential equation. Let's plug in what we had on the previous side. This was the expression for y prime, and this was the expression for y. We can distribute the x plus 2, so that we get, this is going to be the same. So we get x times this series over here. And then we also have 2 times this series, same series. We can move the x on the inside, so that we have a sub n, x to the n plus 1. So again, this is the series from the previous slide. We want the series to have terms with the same power of x. Let's make them all x to the k. Let's shift the summation. In the first integral, let n minus 1 equal x to a equal k, then n equals k plus 1. In the second integral, let n plus 1 equal k, then n equals k minus 1. Third integral is fine, so just replace n with k for the sake of consistency. Again, we want all summands to have generic term x to the k. When we make these substitutions, n is going to be k plus 1. This a sub n will be a sub k plus 1. This n is k plus 1. And n minus 1 is just going to be x to the k. Then we make the substitution n plus 1 for k. In other words, n equals k minus 1. So n is k minus 1. This n is k minus 1. And this n plus 1 is just plain k. And this second series is fine. So we just have 2 a sub k x to the k. Okay, awesome. So this was the series from the previous slide. Let's rewrite this. Instead of k plus 1 equals 0, we could rewrite it as k equals negative 1. Instead of k minus 1 equals 0, let's just write it as k equals 1. Now, all these series have k equals 1 terms. Everything's fine from k equals 1 onward, but we need to pull out the terms before these. Notice this one begins at negative 1. Okay, k equals negative 1. We can't add these series together. They don't begin at the same spot. This guy starts early. So let's pull out the k equals negative 1 term and k equals 0 term. Plug in k equals negative 1 to this formula, and we end up with a sub 0 times x to the negative 1. Well, 0 times anything is 0. Plug in k equals 0 into the formula, and we get a sub 1 times x to the 0. In other words, just plain a sub 1. Okay, so those are the terms that come before k equals 1. It's the k equals negative 1 and k equals 0 terms. This series is fine. That begins at k equals 1. Yeah, this series, notice this begins at k equals 0. So let's pull out a term. So we're going to pull out the k equals 0 term. That's 2 times a sub 0 k to the 0. That's where this comes from. And then what's left is the series 2 times the sum as k goes from 1 to infinity of a sub k x to the k. Okay, awesome. So now all of these indices begin at k equals 1. So we can add these together. So this simplifies to a sub 1, and we had 2a sub 0. That's what the other one simplifies to. So we have, if we move the 2a sub 0 and the a sub 1 together, we have 2a sub 0 plus a sub 1 plus the sum as k goes from 1 to infinity of this hairy expression. That's all going to be 0. Because we compare coefficients on the left and right sides. The constant coefficient on this side is 2a0 plus a1. Constant coefficient on this side, that's just 0. So 2a0 plus a1 equals 0, which means a1 equals negative 2a0. Let's just try to express everything in terms of a0 rather than have a1 and a2 and a3 running around. Now, we compare coefficients on the left and right sides. There's no coefficient of x to the k on the right side, so the coefficient is 0, which means that this coefficient of x to the k must also be 0, because again, compare coefficients on the left and right sides. So we have a sub k plus 1 times k plus 1 plus a sub k minus 1 plus 2a sub k equals 0. In other words, a sub k plus 1 times k plus 1 equals negative a sub k minus 1 minus 2a sub k. Divide both sides by k plus 1, and we end up with a sub k plus 1 equals negative a sub k minus 1 minus 2a sub k all over k plus 1. Okay, this was just copied from the previous slide. This is a recurrence relation for a sub k plus 1. We don't have an explicit formula for a sub k plus 1 in terms of k. It's not like it's sine k over k factorial or something like that. Instead, we have a formula for a sub k plus 1 in terms of previous terms, namely in terms of a sub k minus 1 and in terms of a sub k. That is a recurrence relation where you don't have an explicit formula, you just have a formula in terms of previous terms. Okay, so here's our formula for a sub k plus 1, and we already know that a sub 1 equals negative 2a sub 0. Recall, all we need to know, we just need to know the values of the coefficients for this series, a0, a1, a2, etc., because that's our power series. So, since we already have a sub 1 in terms of a sub 0, let's use this to get a sub 2 in terms of a sub 0. To get this to be a sub 2, we have to plug in k equals 1. So we plug in k equals 1. We get a sub 2 equals negative a sub 0 minus 2a sub 1 over 1 plus 1. In other words, it'll be negative a sub 0 minus 2 times. Okay, now we want just a sub 0s. We don't want to have a0s and a1s and all sorts of other stuff. So let's replace the a1 with negative 2 a sub 0. We saw that on the previous line. So the numerator is just going to be negative a sub 0 plus 4a sub 0. In other words, 3a sub 0. So we have 3 halves a sub 0. That's a sub 2. 3 halves a sub 0. Let's plug in k equals 2 into this formula. When we do that, we have a sub 3 equals negative a sub 1 minus 2a sub 2 all over 2. All over 2 plus 1, I should say. So we have negative 2, negative 2a sub 0, that's 2a sub 0, minus 2 times 3 halves a sub 0. That's going to work out to be negative a sub 0 all over 3. So we have negative 1/3 a sub 0. That's what a sub 2 is. And I think we're done. Sorry, that's what a sub 3 is. So I think we're done, because this sum is going to be a0 plus a1x plus a2x squared plus a3x cubed. In other words, it'll be a sub 0. a1 is negative 2a sub 0, so we have minus 2a sub 0x. A sub 2 is 3 halves a sub 0, so we have plus 3 halves a sub 0x squared. And then a sub 3 is negative 1/3 a sub 0. So we have negative 1/3 minus 1/3 a sub 0 x cubed. Okay, and here's our polynomial approximation to the solution to this differential equation, all in terms of a sub 0.